Okay, we might also connect our RLC networks in series. So you can imagine we'd have some inductance, some resistance, and some capacitance. We place a voltage source, Vn, across them, and of course some current would flow through this RLC circuit. We would develop an inductance, a voltage across the inductor, and a voltage across the capacitor, and of course a voltage across the resistor. Now in this case, our low frequency equivalent circuit is dominated by the capacitor. So at low frequency, our circuit looks simply like this. You can imagine the limit being at DC. The capacitor is an open circuit, so it has the highest impedance. At high frequency, the inductor has the highest impedance. So the inductor dominates. And at resonant frequency, the inductor and capacitor, at least impedance-wise, cancel one another out, and we just have a resistance. If we look at a plot of z of omega, we can calculate z of omega is equal to r plus j times omega L minus 1 over omega C. Of course, at resonance, omega naught, the resonant frequency is where omega L is equal to 1 over omega C. So we can say omega naught is still equal to 1 over the square root of LC, as before. If we were to plot this function versus frequency, plot the magnitude and phase of the function versus frequency, so here's our magnitude. We would see that at low frequencies, the capacitor dominates, and as we increase the frequency, the impedance would reduce until we got to our resonant frequency. As we go above our resonant frequency, the inductor would dominate, and the impedance would increase. So over here, the circuit looks capacitive. Over here, the circuit looks inductive. And we get the associated increases and decreases with impedance. So this would be a minus 20 dB per decade slope. And this would be a plus 20 dB per decade slope. The value at the minimum at the resonant frequency of the impedance would simply be whatever our resistance is. And we desire that to be very small if we want our circuit to have very low loss. Now if we look at our phase response of Z, we know that the circuit looks capacitive at low frequencies, so it would have a minus 90 degree phase shift. In other words, the current would lead the voltage. At resonance, the phase shift would be 0 degrees, and as the frequency increased beyond resonance, it would approach 90 degrees. In other words, the voltage is leading the current. Now, the math for finding these quantities is very similar. So we're going to look for quality factor. And remember, Q is equal to omega times the energy stored divided by the average power dissipated per cycle. Okay, at resonance, when the voltage reaches its peak, the current is approximately I peak is equal to V peak divided by whatever our resistance is. So all of our energy will be stored in the inductor, and we'll have 0 energy stored in the capacitor. So we can say that our E peak value is equal to 1/2 L times I pk squared, energy in an inductor is 1/2 the inductance times the current through the inductance squared, which is equal to 1/2 times L times V peak over R squared. Now the power dissipated by the resistor P sub R, we can say P sub R is equal to I peak squared over 2 times R. In other words, we have the RMS current squared times the resistance. This is equal to V peak squared over 2R, if we want to work in terms of voltage. Finding the quality factor, you say omega naught times 1/2 L times V peak over R quantity squared divided by V peak squared over R. We see that this is equal to omega naught times L over R, which is equal to square root of L over C over R, which is equal to 1 over omega naught times R times C. Here, in order to have a large quality factor, we see that in the series RLC circuit, we'd like to have either a large inductance or a small capacitance, and in either case, we'd like to have a small resistance. Now here, what we would find is that the branch voltages, the voltage across the inductor and capacitor at resonance, VL is equal to VC, is equal to Q times the input voltage. Again, this can be very large. And one thing that we have to be careful about when we start using these in circuits is we have to monitor these voltages to make sure that they don't get so large that they can cause damage to transistors or other circuitry. If we look at the bandwidth of this circuit, it's very similar to the bandwidth for a parallel RLC circuit. We can show that Z of omega near resonance is approximately equal to R plus J times 2 times delta omega times L. So this is near resonance. And we would also see a bandpass response centered around omega naught, our resonant frequency. Where if we measure the 3 dB bandwidth of the circuit, we would find that the bandwidth was equal to R over L. And if we normalize this to omega naught, normalized bandwidth is equal to R over L over square root of, over 1 over the square root of LC. And we would find this to be equal to 1 over the quality factor. In other words, we can say that Q is equal to omega naught divided by the 3 dB bandwidth of the circuit. Now, as before, if we have a small Q, we have a large bandwidth. And if we have a large Q, we have a very small bandwidth. Alright, so we'll look at some examples of RLC circuits in class.